Welcome back to linear algebra. In this video, I'm going to talk about the range of a linear transformation. Remember from a previous video that a linear transformation is a function, I'll denote it as L, which maps from some set we call the domain. I'm going to use Rn as my domain, a vector space, and then the codomain, Rm, is a different vector space. Could be the same vector space, but in general, we're going to assume that they have different dimensions. And a transformation is linear if it has certain behaviors around linear combinations of vectors. The result that we came up with from that previous video is that if a transformation can be represented by multiplication by a matrix, then it is a linear transformation. And if it's a linear transformation, you can always form this matrix. I talked in that video about how we're introducing this idea of the codomain to tell us the kinds of vectors that come out, right? My L here brings in n-dimensional vectors and spits out m-dimensional vectors. But when we talk about functions, very often we care about being a little bit more precise. Which m-dimensional vectors can actually come out of this function and which ones are kind of stuck behind? We call that idea the range of the function. It turns out that the range of a linear transformation is a vector space, or at least it can be a vector space if we use that term a little bit more loosely. To understand what I mean, I want to look at some relatively easy examples using the three-dimensional space that we live in and the two-dimensional space that you are watching me on, the screen of your computer, tablet, or whatever device you have. When you think about three-dimensional space, you can think about a two-dimensional plane being embedded in that space, right? The space with the x direction, generally speaking, x is towards you, the y direction, which would be over this way, and the z direction going upward. And if you take the xy plane, that is the two-dimensional space that we're used to using with graphing. You could also take the xz plane, which is the one kind of this way, or you could take a plane that goes on some sort of a diagonal. So a relatively straightforward way of dealing with that is to take x vectors in xy space and make them x vectors in xyz, take y vectors in xy and make them y vectors in xyz, and you get this plane, which is the origin. You can also take that idea and kind of tilt it on its side. I'm not going to try to find specific vectors that work to do this, but you could imagine kind of a plane that kind of sets off at an angle. All right. For reasons that we're not quite going to get into today, but we're going to talk about a little bit later, one thing that we're always going to insist on is that the plane goes through the origin in space. And the reason for that is a pretty straightforward theorem. where I claim that for any linear transformation, if you evaluate that transformation at the zero vector, you get out the zero vector. The proof of this is very straightforward. Because in any vector space, for any vector v, 0, the scalar times v is equal to the zero vector. So that means that the linear transformation of the zero vector is the linear transformation of 0 times some vector v. And since it is linear, that means it's 0 times the linear transformation of v, and 0 times any vector is the zero vector. All right, so we are going to be sure that our planes always have to go through the origin when we're talking about this. But we could also take this down a notch, I guess. Instead of a two-dimensional result, we could get a one-dimensional line passing through the origin. Right? It looks like this particular line is something like -1, 1. And so we can mark out spots along this line going forward and backward in time and get to various points that way. All right, so that's the basic idea I'm talking about. If we take a three-dimensional space and we look inside it and we restrict down, we can get a two-dimensional plane or we can get a one-dimensional line. Those are the visualizable options here, but that idea extends to any number of dimensions. If we have a four-dimensional space, we can embed a three-dimensional space inside it in any one of several orientations. If we have a 27-dimensional space, we can embed a 19-dimensional space inside of it. We call those ideas subspaces, and that's really what we want to focus on today. But I did want to lead off with the idea here is that the range of a linear transformation is going to be a subspace of this sort. So let's take some set V, which is a subset of a vector space, in this case, the n-dimensional vector space. We will call V a subspace if and only if two conditions hold true. The first condition is that the zero vector must be inside the space. The second condition is that V is closed under linear combinations. All right. And once again, depending on your background, you may or may not have come across the idea of the closure of a set before. When we say that a set is closed under an operation, what we mean is that if you take things from the set and you perform that operation, the result is another thing in the same set. So in this particular case, what we mean is that for all v1 and v2 in our set V, and constants c1 and c2 in the real numbers, the linear combination c1v1 plus c2v2 is also in set V. Right. If that is true, if we have that the zero vector is inside the set, and we have that it's closed under linear combinations, we're going to call that set a subspace. And as we'll see throughout this video, we can treat the subspace as its own vector space. And most of the things that we want to do with vector spaces are still going to work very nicely. The only thing we lose is being able to write the vectors in a nice column notation, but even that we'll get back about another half of the way through the course. All right, so let's take a look at a couple of quick examples. All right, consider a set of vectors in R3. All right, from the definition of this set, we can see clearly that V is a subset of R3, and R3 is, of course, a three-dimensional vector space. And then we have the two conditions. X is equal to 3y, z is equal to negative 2y. And if you notice here, if I set y equal to 0, that means that x is equal to 0 and z is equal to 0, just directly from the definition, which means that the vector 0, 0, 0 is in V. And 0, 0, 0 is, of course, the 0 vector in R3. So that's the first condition down. For the second condition, let's pick a couple of vectors, v1 and v2 in V. And we'll pick a couple of scalars, c1 and c2 in R. Using the definition of set V, if vector v1 is in set V, that means that there is a y such that x is equal to 3y, z is equal to negative 2y. The easiest way to write that is that v1 is the vector 3y1, y1, negative 2y1. And likewise, v2 is 3y2, y2, negative 2y2. All right, now mark down that I can do that by definition of set V. It is the definition of this vector space that allows me to achieve that. And to talk about a subspace, we're talking about linear combinations of these vectors. So let's consider c1v1 plus c2v2. Let's plug in that v1 is 3y1, y1, negative 2y1. Let's plug in that y2 or that v2 is 3y2, y2, negative 2y2. And let's go through and do the algebra from here. For the sake of time, I'm not going to go through and write out every step. but you can do the scalar multiplication, you can do the vector addition, and you end up with a thing that looks like this. And then from here, I'm going to factor out just a little bit. And notice that I can group together a C1y1 plus C2y2. In all three terms. And technically speaking, that's actually all I need. But I think it becomes a little bit more obvious if I introduce a new variable. Let's let y3 equal C1y1 plus C2y2. And that way I can rewrite my linear combination as 3y3, y3, negative 2y3. And at that point, it should be very obvious that this is an element in my vector space V, which is exactly what I wanted to prove. All right, so this particular set is a vector subspace. All right, it is a subspace of R3. It's not a vector space in the way that we think of it, because we can't just write down any vector and know that it's going to work based on the dimension. But again, that's something that we'll build to a little bit later on. For now, it is a subspace, and that's a lot of information for us. Right. To illustrate that subspace actually is kind of important, it's not something that is very easily achieved. Let's take a look at another set that was going to look incredibly similar to that last one. Consider the set of x, y, z vectors in R3 such that x is equal to y plus 3 and z is equal to y minus 2. So we'll add and subtract instead of multiply. And that much of a difference actually makes it so this set is no longer a vector subspace. We can show that it breaks down on either step. This particular set does not have the zero vector, and it is not closed under linear combinations, but showing that it doesn't have the zero vector is a little bit more elegant. If the zero vector were in this vector space, then it would be the case that 0 is equal to y plus 3, 0 is equal to y, and 0 is equal to y minus 2, which means that y is equal to negative 3, 0, and 2 simultaneously. And I hope you will agree with me that this is absurd. And because this is absurd, that means that 0 is not in my vector space, or in my set V. And so V is not a subspace of R3. All right, so subspace is a big deal in some way, shape, or form. And that's going to be of use to us. It turns out that there is a very convenient way of establishing a subspace that will always work. If I take a set of vectors, a relatively small set, here I have k vectors in Rn, then it will always be the case that the set formed by the span of these vectors is a subspace of Rn. Remember that the span of a set of vectors, let's call it capital S just to give it a name. And I don't even have to get that creative with things. But this span is the set of all the linear combinations, C1U1 plus C2U2 down through to CKUK. And if I just pick the specific values, C1, C2 down through to CK are all the real number 0. And I take the linear combination with that, I get the 0 vector, which means that the 0 vector is an element of the span. And that's half the battle. The other half of the battle is linear combinations. We've actually already proven that a linear combination of linear combinations is a linear combination of the vectors that make up the linear combinations. But stating that kind of makes me go cross-eyed. I don't know about you. So let's pick a couple of vectors, v1, v2 in S, and let's prove this again. By the definition of S, we know, of course, that v1 is a1u1 plus a2u2 plus all the way down through to ak uk. And v2 is some other string of constants, b1u1 plus b2u2 plus all the way down to bk uk. I don't want to use C because I want that to be my string of constants that I get in the end. I could use D. I don't want to use E because we might get that mixed up with the natural number 2.71828. If I start using F or G, you might start thinking functions. So we're running low on letters. Let's take P times V1 plus Q times V2 as a linear combination. Well, that's P times A1 U1 down through to AK UK, and then Q times B1 U1 down through to BK, UK. And using rules for rearranging things, I can distribute PA1U1 down through to PAKUK, QB1U1, all the way down through to QBKUK. And then I want to regroup things so that all of my U1 terms are together. So PA1U1 and QB1U1, and all the way down to PAKUK plus QBKUK. And then I can factor out the vector. Factor out PA1 plus QB1 all times U1. Factor out PUK plus BUK all times UK. And technically speaking, we are done, but as we saw previously, if we introduce some new constants, I'm just going to do a generic term. CI is equal to P times AI plus Q times BI. For I goes from 1 to K. Then we can rewrite this more explicitly as C1U1 plus all the way down to CKUK, which very clearly is an element of set S. All right, so we showed that set S has the zero vector. We showed that set S is closed under linear combinations. That's what it takes in order to say that the span of a set of vectors is in fact a subspace of whichever vector space those vectors came out of. Now, having any set of vectors which can produce a vector space by the span is very nice. It turns out that things get even nicer if we can find a linearly independent set of vectors whose span is the entire vector space. A little bit later in the course, I'm going to come back to this idea and show you that it is possible, given any set of vectors, to reduce that set of vectors down to a linearly independent set whose span is the same vector space. But the span of any set of vectors is a vector space. There is always a linearly independent set that will span that vector space. And in fact, a couple of results I want to give you that I'm not going to take the time to prove. Every vector space has infinitely many such basis sets, or sometimes sets of basis vectors. And the more important one, every set of basis vectors for a particular vector space has the same number of vectors. The properties of any vector space are such that there is a specific required number of basis vectors. If you have more vectors than that, it is not linearly independent. If you have fewer vectors than that, it does not span the entire vector space. That is something we're going to come back and prove quite a bit later in the course. For right now, we're going to take it as gospel because it does allow us to define that important characteristic. The dimension of the vector space is this number of basis vectors that are required. To think about dimension, I want to call your mind back to the examples I was talking about at the beginning of today's video. If you think about a two-dimensional subspace of three-dimensional space, it took two vectors, right? The xy plane. We mapped the x vector in the xy plane in xy space and in xyz space. We also mapped the y vector. We had two vectors to form two-dimensional space. When we talked about the line, we needed just one vector to describe it. And that always does work. Anytime you are talking about a one-dimensional vector space or subspace, you're talking about a line embedded in a higher dimensional space. Anytime you're talking about a two-dimensional space, you're talking about a plane embedded in higher dimensional space. Three-dimensional space is the space we live in. Four-dimensional space, you can think of as space-time if you want to get technical, but at that point, visualizing them starts to break down a little bit. All right, so the word dimension means exactly what you think it means. And that's a property that we're going to be using and building on quite a bit throughout this course. For now, let's take these ideas of vector spaces and subspaces and come back to the properties that we wanted to talk about from the beginning. The range of a linear transformation, or the range of a matrix transformation, which is going to be a little bit easier to think about. So for any matrix A, I'm going to specify M by N so that I can talk about things a little bit more. But the row space of A is the name we give to the vector space formed by the span of the row vectors. So if we have a vector, an M by N matrix, the row space is a set of n-dimensional vectors. There are m of them. And we take the span, which could be, since they are n-dimensional vectors, it could be an n-dimensional vector space, or it could be smaller, because we have no idea, given a random matrix, whether the rows of the matrix are linearly independent or not. Likewise, the column space is the space formed by the column vectors. Each column of A, there are n columns. Each column has m dimensions. So this is a set of n m-dimensional vectors. It could be that the column space of A is an m-dimensional vector space, or it could be smaller because we have no idea at the start whether the column space or whether the columns are going to be linearly independent or not. So remember, if the vectors are linearly independent, then the span or the dimension of the span is the number of vectors. If the vectors are not linearly independent, that means that we could remove vectors and have the same span, so the dimension of the space is slightly smaller. All right, how about a lemma? I don't think I've done a lemma yet in this course sequence. A lemma is the name we give to a theorem, which is not a very useful theorem on its own, although that's kind of bad to say. Lemmas are the most useful theorems. It's just that actively using them is difficult because they are highly technical, they are highly specific, and they talk about situations that you don't feel are going to come up very much. They are the most important theorems because we are immediately after proving one or more lemmas going to prove a more profound theorem, and most of the work is going to be, hey, remember that lemma that we proved before? Yeah, it applies here in this case that we contrived in the middle of the proof. All right, so as we're looking at this theorem, if you feel as though you aren't quite sure how it applies, that's perfectly fine. That's how you should be thinking about it. Let's take two matrices A and B, and I want them to be row equivalent matrices. Remember that row equivalent means that if we start with A and we perform one or several elementary row operations, we can get from A to B. And as long as that is the case, I claim that the row space of A and the row space of B are the same vector space. And I've made a note here that I'm going to denote the row space of A, R of A, the row space of B, R of B. Just a convenience of notation as I work through this proof, which is, again, kind of technical, because why are we going to be comparing the row space of row equivalent matrices? Because in the next theorem, it's going to turn out useful to talk about row equivalent matrices in the middle of the proof. Other than that, this lemma actually isn't of much use. But using the definition of elementary row operations, because these matrices are row equivalent matrices, that means that we've performed several elementary row operations, and elementary row operations are linear combinations of the rows. So the rows of B are linear combinations of the rows of A, and another result from that, the rows of B must all be vectors in the row space of A. Remember, the row space of A is the set that is the span of the rows of A, the set of all of the linear combinations. And another nice thing about row equivalent matrices is that elementary row operations are invertible. Every elementary row operation that is done can also be undone. So I'm just going to say likewise here. It's the exact same argument. The rows of A are linear combinations of the rows of B. That means that the rows of A are vectors in the row space of B. From here, things get a little bit crunchy and a lot a bit abstract. I'm not going to keep trying to write things down because I'm not entirely sure if it's worthwhile. But we know that the span of a set of vectors is closed under linear combinations. So if all of the rows of B are in the row space of A, that also means that every linear combination of the row space of B is in the row space of A. And we can express that as a subset. I'm going to write that since vector spaces are closed under linear combinations, the row space of B is a subset of the row space of A, and the row space of A is a subset of the row space of B. Again, this is piling all of our definitions together. This is definitely one of those ones. It should make sense in the sense that you can follow and you can agree that the logic is true. It doesn't have to make sense in the viewpoint of, I'm never going to ask you to perform this kind of argument in a proof on your own. At least in this class. If you're moving onward to take more mathematics, it might come up in a future class. But using the fact that the row space of B and the row space of A are spans of sets of vectors, and spans of sets of vectors are closed under linear combinations of vectors in the span, it must be the case that if we have a set of vectors B, the rows of B, that are in the row space of A, then the span of those vectors, the row space of B, is all in the row space of A, and we can do the same argument in the other order. Finally, by subset inclusion, the row space of B is equal to the row space of A. I'm not sure if I've talked about subset inclusion in this course previously, but it's a fairly straightforward idea that is basically what we just have here. If you have two sets where one is a subset of the other in both directions, the only way you can have subsets in both directions is if they are the same set. Right? Depending on the math classes you've taken previously, you may have seen the idea of subset inclusion in the past. It's something that I bring up in calculus courses. It's something that also shows up in discrete mathematics. If you've not seen subset inclusion before, you might have seen something very similar with inequalities. If A is less than or equal to B, and B is less than or equal to A, the only way for both of those inequalities to be true is if A and B are the same thing. That's literally the same idea we're talking about here. We're just using the set relation instead of the inequality relation because we're talking about sets instead of numbers. Sorry about that. Anyway, that gives us the proof of this lemma. Again, definitely a complicated technical lemma. Where are you going to see the need for row equivalent matrices to have the same row space? Well, you're going to see that need when we try to prove this theorem. Let A be any matrix. The row space of A and the column space of A have the same dimension. We're going to call this dimension the rank of A, and often we're going to write it in function notation rank of A like that. Before I get into this proof, I do also want to mention that because a linear transformation can be written as a matrix multiplication, We'll also use this vocabulary to talk about the row space and the column space of the linear transformation defined by multiplication with matrix A. So you'll also see the rank of a linear transformation. It is this exact same number, right? And it's the exact same definition, right? If we're talking about the rank of a linear transformation, we're saying write the linear transformation as a matrix and find the rank of the matrix. And once again, one of those proofs that if somebody hadn't shown me this, I have no idea how I would come up with it on my own. But someone did show me it, and it is absolutely brilliant. And now that I know it, I'm able to reapply it to other things. I don't necessarily expect you're going to get that far this semester, but if you continue on with your study of mathematics, it's going to be a process that actually comes up more often than you would think. But I'm going to introduce a new matrix R, which is the reduced row echelon form of matrix A. And the reason that we prove that lemma is so that I can say that once I get A into its reduced row echelon form, the row space of R is the row space of A. Now I'm going to use some properties of reduced row echelon form. Matrix R has some zero rows. It's possible that your reduced row echelon form has no zero rows, but in general, we can assume some of the rows are zero. I want to ignore the zero rows and only consider the non-zero rows, which I claim are linearly independent. I can make that claim from the simple perspective of performing elementary row operations is taking linear combinations. And if there was a way to take linear combinations of the rows that are left and get the zero vector out, we would do so and we would have another zero row. So because we're not doing so, we don't have another zero row. The rows must be linearly independent. And the span of that set of linearly independent rows is the row space. And since they're linearly independent, that also forms a basis. The number of linearly independent rows is the dimension of the row space. Also thinking about properties of reduced row echelon form. When you have a matrix in reduced row echelon form, there is some leading zero. And I don't care about what else comes down. But wherever that leading zero is, or sorry, wherever the leading one is in a row, the rest of the rows under that column are zero. And if another row has a leading 1 somewhere else, everything above and below is 0. That's what it means to be in reduced row echelon form. All right, so in this particular case, I set this up so that my matrix has 3 non-zero entries and 3 leading 1s. The properties of reduced row echelon form tell us that the column which has the leading 1 is going to be one of the basis vectors for, one of the standard unit basis vectors, EK, right? So in this case, I have E1, E3, and E4 in 4-dimensional space. It could be different ones, that doesn't matter. What matters is that they are all those basis vectors. And those basis vectors will, or those vectors will form a basis for the column space of R. Because every other column is going to have a non-zero entry in the rows that have a leading 1. And if the row doesn't have a leading 1, that means that everything in the row is 0. So every other column can be written as a linear combination of these just because that's how it has to fall in, right? The reason that we call the standard unit vectors the standard basis is because any other vector can be written as a linear combination of them. Right. Ones are really easy for that. All right, so the row space and the column space of R must have the same dimension because every row that is a non-zero row has a leading entry. Every leading entry corresponds to one of the basis vectors of the column space. The number of basis vectors in the row space and the number of basis vectors in the column space must be the same. The row space and the column space have the same dimension for matrix R. Getting that conclusion into matrix A is a little bit crunchier, but it does absolutely work. To get there, we're going to have to think a little bit about how elementary row operations affect the columns of a matrix. And it's definitely a little bit abstract, but as you perform these linear combinations, it's going to change the relative values of the column vectors, but it's going to change them all in the same way, right? Whatever you do to the third entry in one of the column vectors, you're doing something proportionally in all of the other column vectors. So because we do things proportionally like that, that's how I can claim that even though the column space of R and the column space of A are not the same vector space, the column vectors that became the basis vectors of the column space of R will serve as basis vectors for the column space of A. And since we have the same number of vectors in the basis, the dimension is going to be the same. All right, writing that out, a little bit tricky. I'm going to write it the set of column vectors of A that become the set of basis vectors for the column space of R will serve as a set of basis vectors, the set of basis vectors for the column space of A. Sorry about that. All right, so again, the column space of R and the column space of A are not the same. The set of basis vectors for the column space of R and the set of basis vectors for the column space of A are not the same. The similarity here is that they are the same columns. So if it's the first, third, and seventh column of R that forms a basis, then it will be the first, third, and seventh column of A that forms the basis there as well. All right. So now the dimension of the row space of R, the dimension of the column space of R, the dimension of the column space of A are the same, and the row space of R is the same as the row space of A. So the dimension of the row space of A is equal to the dimension of the column space of A, which is what I said I was going to set out to prove. Right. And as is often the case with proofs at this level, the result itself is interesting. Some of the things we say along the way are also interesting. This conclusion here, for example, we can use that in order to find a way to find a basis for the column space of a matrix. Right? If we have a matrix and we need to find a basis for the column space, we can take the matrix, we can reduce it to reduced row echelon form using elementary row operations. We can take note of which columns form the basis vectors because they are the leading entries in reduced row echelon form, and then take the columns in the same position at the original matrix, and those will be the basis for the column space of the original matrix. When we need it, that's a valuable tool that we can keep in our back pocket. Often, honestly, most of the time, knowing the dimension is going to be good enough for our purposes in this course. All right. Finally, with that, let's consider a linear transformation L defined by multiplication with a matrix. The last theorem, the thing that we wanted to talk about this whole time, the range of the linear transformation is the column space of the matrix. This proof I'm not going to get into in too much depth, but let's consider an M by N matrix, and let's define it by its columns. U1 through UN are going to be the column vectors of A. Then if I take A times some vector V, which I'm going to introduce by the entries, right? A is an m by n matrix, so we can multiply it by a vector in Rn, so v1, v2, down through to vn. We've seen in the past that matrix multiplication is always, or matrix multiplication times a vector is going to give us a linear combination of the columns. And a linear combination of the columns is something in the column space of the matrix. All right, so that brings everything together. That's all of the tools we've been looking at. We understand that a vector space can have a vector subspace. We understand that we can use the span of a set of linearly independent vectors to describe that space. And we understand that if we take the column space, if we can find the span of some linearly independent vectors in the column, that's going to give us the range of the linear transformation. And I mentioned, even though we didn't get so far as seeing an example, that if you take a matrix, you bring it into reduced row echelon form, and you mark down which columns have the leading entries, the corresponding columns in the original matrix are the vectors that make up a basis for that column space. And that's what we need in order to get everything done. This video is run probably longer than I intended it to, so instead of going through several examples, I'm going to give you one to try on your own. So I want to look at the same linear transformation we used in the previous video. We'll define it by its action on the basis. L on E1 is 2100, L on E2 is 3210, L on E3 is 4321. I want to find the dimension of the domain, the codomain, and the range of this vector space. And if you can find the dimension, that's going to be all I really care about. But I would like to take things a step further and actually find a basis for the range as well. The domain and codomain, you should be able to find a basis without thinking about it. But I will go through and find a basis for the range as well in my solution video. All right, take a few minutes, see what you can do with that one, and I'll see you in the next video.